think we can start. Welcome everyone to the first Acodis machine learning themed webinar titled Beyond OCR, Discover the Latest AI Breakthroughs. We are glad that you can all join us on this sunny autumn day. My name is Timothy Mann. I am the head of machine learning at Acodis, and I will be your moderator today. We have a wonderful morning planned for you all, a good mix of academic and industry talks on the latest in research and applications from the field of document AI. We start after this introduction with a talk from Professor Andreas Fischer, who will present selected research projects in his group that are related to document analysis and handwriting recognition. We will then continue on the academic track with a talk from Lars Hillebrandt, who will present KPI BERT, a system which employs novel methods of named entity recognition and relation extraction to extract and link key performance indicators, for instance, revenue or interest expenses of companies from real-world German financial documents. We will then switch to the industry track with two talks from our own experiences. First, a talk from about the applied research approach that we have chosen to do on table recognition by our machine learning engineer, Moritz Blascher. And finally, a talk about the real-world example of extracting and structuring batch records by Severin Kappeler, our technical product manager. All talks are scheduled to take about 10 minutes with 5 minutes of questions and answers at the end. Questions can be posted in the Q&A chat in Zoom at any time, so don't hesitate to do so. I will keep an eye on the chat at all times. We will also send out a short survey later at the end of the talks, so don't forget to fill that out too. So now, without further ado, I have the pleasure to introduce our first speaker. We are honored to have Professor Andreas Fischer as our first speaker. Professor Fischer has both a master's and a PhD from the University of Bern, Switzerland. Afterwards, he conducted postdoctoral research in Montreal, Canada at the Center for Pattern Recognition and Machine Intelligence and at Polytechnique Montreal. Currently, he is full professor at the University of Applied Sciences and Arts, Western Switzerland, and lecturer at the University of Fribourg in Switzerland. His research interests include pattern recognition, deep learning, graph-based methods, document analysis, and handwriting recognition. He has published over 100 peer-reviewed articles in international journals and conference proceedings on these topics. In this talk, Professor Fischer will present selected research topics in his group that are related to document analysis and handwriting recognition. I'm looking forward to gaining an insight into the current state of the art, challenges, and opportunities in this field. I give you the word, Professor.
Thank you very much for the introduction. Let me share my slides. And here we go. Yeah, welcome everyone. It's difficult to convey something like a state of the art in 10 minutes, but I will do my best to give some insights on what is happening at the moment that goes beyond OCR. And to tackle this question, I think it's good to think first about what's actually possible with OCR and what is not. So this is my slide on that topic. It's certainly debatable, but I think what is considered as solved in the way of 99.9% recognition accuracies at the character level is only one particular scenario. Printed documents with modern print, known font, some Arial, Times New Roman, etc. Relatively simple layout, like a newspaper article in column or an address field, and also a high scan quality that transforms a document into a digital image. So if any of these conditions is violated, I would argue today that it's actually unsolved. It doesn't mean it's impossible to do. It just means we are not at 99.9% yet, and it's indeed a very active field of research. And if you want to have a good impression on what researchers are thinking about at the moment, I can recommend to follow one particular conference, which is the International Conference on Document Analysis and Recognition. It exists since about 30 years. It has a long-standing tradition, held every 2 years, at least until 23. And then it will become actually an annual event, which also indicates the speed of research, the number of research activities around these topics. Last year, we had the pleasure to organize this conference for the first time in Switzerland. So a few selected topics from our own group that, of course, far from being exhaustive of possibilities to go beyond OCR. But I think one traditional aspect is handwriting recognition. We would all agree that this is an unsolved problem. We are currently working on this topic here on an electronic edition of letters sent to and from Heinrich Bullinger, an important Swiss reformer. And as you can see in this example letter, even for humans, it's really difficult to understand what is written in these letters. It's a mixture between German and Latin, a lot of abbreviations. So you can also see the layout, the baselines, etc. Really challenging topics. Nevertheless, we get quite good performance. Good means, let's say, below 10% character error rate when combining deep convolutional neural networks these days, recurrent neural networks, attention mechanisms, notably transformers, and also synthesization of handwriting to give the model a better understanding of the variations of the different handwriting styles. Another topic of interest, so this was a work of one of my PhD students that's already finished, is still signature verification. Today, it remains a very important means of biometric authentication. Also legally accepted and easy to use. So this also requires, from the pattern recognition point of view, automatic methods to help with the verification. In difficult cases, of course, a human has to help, but in many cases, an automatic method can be of help, let's say. And here, the deep convolutional neural networks are working well, as in other domains. However, the problem is that we have a lack of data. So this is a small data problem. Every user contributes 3 to 5 signatures, and you need to model that. And here it was necessary to combine the deep learning approach with a more structural analysis of the handwriting by means of graphs. Finally, to get more modern handwriting into the mix, we are also working on digital ink, that is handwriting that is written on let's say, iPhones, tablet computers of any sort, professional Wacom tablets, or Microsoft Surface, anything that records the handwriting, not only as an image, but also over time. So we know where the pen moves, we have the stroke order, and we also have the velocity information, so this should actually be easier to recognize. There's still many open problems. This is an ongoing project that we're doing together with Google. The idea is that you have some online writing and also its transcript. And the question is, where does a character start and where does a character end? So in this example, it's clear, as indicated in the colors to the right. You can see the individual characters. It gets more complicated for cursive handwriting, for other scripts and languages, Arabic handwriting. We also tested it for Vietnamese handwriting with a lot of accents and delayed strokes. And again, a very good method for this problem has turned out to be structural deep learning with attention mechanisms, notably transformers. Why we are doing that, or why Google is interested in that, it's if this problem is solved sufficiently, a large database of characters can be built. And it illustrates also a bit the fundamental problem of handwriting. In order to recognize it, you need to segment. And in order to segment, you need to recognize. So it's always good to approach the problem from both sides at the same time. But all of these examples are still focusing on the recognition, be it in historical documents or modern digital ink, getting the character from an image or from a trace. However, in my opinion, if we are talking to go beyond OCR, and I saw that today's topics cover that as well, we need to go beyond the recognition as well and towards document understanding. And here I would say research is still somewhat in its infancy. So a document is a communication from a human to a human. And the goal is really to understand that communication after we have recognized the different contents. We have worked on that in a recent project in the context of circular economy. Here the goal was to read the website of a company and to understand what it is that the company does. So what is the most important product? What are the processes going on in that company? And this information, this understanding was then inserted into kind of a matchmaking system that helps to find new innovative ways how to link companies in a circular economy, especially how to use the waste products of one company as an input for another. And this originally started as a European research project, but we are now continuing that also with a German startup to build it up as a as an applied research example, let's say, in Europe and maybe even beyond. So with that, I hope that I could at least scratch a bit the surface on state-of-the-art current problems, challenges, but also opportunities in document analysis. And I'm happy to take some questions.
Thank you very much, Professor Fischer, for this excellent talk. Yeah, I know it's very hard to do that state-of-the-art summary in 10 minutes. So I'm sure there are a lot of open questions. So feel free, our participants, to put them in the chat. Let me start by asking a few questions regarding, for instance, handwriting recognition. That seems like a problem that is definitely in the few-shot, one-shot domain. Are there any latest development in that field that helps solve this problem?
Yes, so when you're talking about one shot or few shot, the idea is that you open a new manuscript that you have never seen before, and you want to do, for example, keyword spotting, which is indeed a very important part of handwriting recognition. And I'm aware of recent work that tries really to avoid any kind of manual labeling of the data, which is the real challenge here, because it's costly and difficult to get labeled data, that is the handwriting image together with the label, what is written on it. Sometimes you need experts for the language, for the script. There is so many different manuscripts yet untouched in historical manuscripts that it's nearly impossible to get labels for all the different scripts and languages. And it's indeed possible. So even with deep learning, and the one trend that I could observe in recent years is really to start with printed fonts and then somehow learn first the print, which is kind of the core structure of the writing, nevertheless, with the topology information, where are the loops, where are the crossings, the T's, etc. And then gradually adapt it in an unsupervised fashion to the handwriting at hand. So I find that quite exciting. So in this particular project here, we actually have still a training set of about 150,000 lines. So this is not a few shot problem, but the big challenge here is that some of the letters are written, some people have contributed only 1 or 2 letters. So that there are some writers that we don't know, where the style is unknown, and then we need to rapidly adapt to that style. So it's again a question of adaptation.
Yeah, excellent. I think everybody in this field has problems with the lack of labeled data. We can talk about those experiences ourselves. And then another question I had that is maybe close to my heart. It's about the digital ink. Obviously, so my background is in Chinese, and I was wondering if there's also research being done in recognizing written Chinese characters, because those are usually very complicated, especially in the traditional script that is common in Taiwan and Hong Kong. And I was wondering if there's also some interest in the Western world, outside of China and Southeast Asia, that is doing these kind of things, and maybe if there's some learnings that can be had that can be shared.
Yes, so there's we have a very strong participation of Chinese researchers actually on the topic. For example, Professor Chenglin Liu has a very large team of researchers who contribute at every hectare new insights into Chinese handwriting. And it's interesting because it's a very structural problem. And the stroke order is also very standardized. And this has led to some particular approaches which work well for Chinese, which are maybe not transferable directly to the English cursive handwriting. But nevertheless, the methods converge in a certain way. As we all know, it goes from translation to automatic writing to Chinese handwriting recognition. The technology converges, so there is a very good exchange on that topic. I have worked in the past years on ancient Vietnamese handwriting, which is not used anymore, and which is also logographic writing that shares similarities with the Chinese writing a lot. And this is also one aspect that I've mentioned before, where the printed font has turned out to be an excellent guide towards understanding, recognizing handwriting, which is maybe less the case for handwritings such as that of Heinrich Bullinger, that's very cursive, very connected, etc. So here the font is far from what you can observe in the handwriting, but for the Chinese handwriting, this was our experience at least. The structure is so important because there are so many different characters that every detail is important, and these details, they're present in the printed font.
Yeah, this is cool. That's very good to hear. that there's definitely research being done in that field too. I don't think there are any other questions open in the Q&A. I would like to thank Professor Fischer again for this excellent talk, and we'll go on with the next speaker. Thank you, Professor. So our second speaker is Lars Hillebrand, coming from the Fraunhofer Institute for Intelligente Analyse and Informationssysteme and the University of Bonn, where he's currently a PhD student. He is a data science and machine learning enthusiast with a focus on NLP, and has already published multiple research papers and completed business projects in the area of information and relation extraction, text matching, topic modeling, etc. He will talk today about his recent paper called KPI BERT, a joint named entity recognition and relation extraction model for financial reports. And I'm curious to hear if his solution is the first step to make financial analysts obsolete. Lars, you have to.
All right. Yeah, thanks a lot for the introduction. Let me go to full screen here. Yeah, first of all, thanks for having me, and good morning, everyone. Just as a little background, I met actually Moritz at the International Conference of Pattern Recognition in Montreal this year. And yeah, that's how I ended up here. He was listening to this presentation already and moderated it. And yeah, we got in touch, and I'm very happy to share my joint work with some colleagues here in this round as well. So looking forward to it. All right, so as I hinted at already, this is joint work, not only with other colleagues from Fraunhofer and the University of Bonn, but also with our industry partner, PricewaterhouseCoopers. And yeah, let's get right into it. So as told in the introduction, we developed a new named entity recognition and relation extraction model, which we titled KPI BERT. And it's particularly used in the context of financial reports together with PwC. And yeah, let's get into it. So just to give you a little bit of a background, what are we looking at here? So the goal is to understand financial reports better. Now, why are financial reports important? So as you might know, companies are forced by law to regularly publish financial reports where they basically tell the public about their economic well-being, about their financial health, about lots of important information about the company so that outside investors know as good as possible what is going on. And since this is quite important, the company obviously cannot write what it wants to write. It has to follow very strict accounting standards like IFRS, the International Accounting Standards, or the GAAP standard in the US. And how do we know that the company actually fulfills these requirements? Well, that's where the auditors come into play. They obviously have to then check manually these long reports that typically span up to multiple hundred pages for their correctness, completeness, and so on. And as you can imagine, this is quite time consuming. And this is why we, together with PwC, try to leverage pattern recognition and machine learning in order to improve this entire process. And specifically, where does KPI BERT come into the picture? Particularly, our system tries to basically automatically extract what you can see in the top left screenshot here on this slide. So that is a screenshot of a page of a financial report. And as you can see on the top left, there is a large body of text where the company writes quite in detail about many different so-called key performance indicators like total assets, current other financial liabilities, and so on. And it also names the numeric quantities for the current year, the prior year, and so on. And the goal is here from these unstructured written sentences to basically detect and relate these KPIs with their numerical values automatically. And the idea, of course, or the motivation for that is that once you have this information automatically extracted, the auditor can directly use it without finding it himself, which enables quicker cross-checking and in general time efficiency gains. Here is a very concrete example. Namely, you see a sentence, and in green, we see what our named entity module of KPI BERT outputs in a first step. So the model basically traverses the sentence word by word, and we see for each word whether or not it belongs to one of our entity classes that we're interested in. This is not specifically new. However, here, we can see, of course, then that revenue is tagged as KPI, 100 as current year, and so on. One note, though, is that the model only currently extracts the 100. We're not really interested in the million or billion. Why? Because this is extracted prior to the actual machine learning part via some pre-processing, some regexes. So here with rule-based methods, we can, with a basically 100% accuracy, link these units to the number. So we don't need to focus on this particular issue also with the machine learning. In the bottom, you then can see what the relation module is doing. Eventually, we obviously want to know, okay, now which entities, which KPIs, current year values, and so on that we extracted are actually connected. So the relation extraction module then takes these entities and tries to draw edges between those, link them, basically. All right. I quickly want to put this work a little bit into perspective, into what else is going on. So our collaboration with PwC goes back already to like 5 or 6 years, where joint work on the so-called ALI tool started, which is short for Automated List Inspector. And this is actually a full-fledged auditing tool by now, which is used in 3-4 different countries, where auditors can upload full financial reports that you could see in the screenshot here on the right. And then depending on which report it is, certain requirements have to be fulfilled. These requirements have to be, they are rendered automatically on the left. And the auditor can then select specific requirements. And then in the center, the tool automatically suggests the relevant passages in these 100, 200 page long reports, so that the auditor doesn't need to search for the specific passage which a requirement relates to. So this was the original idea of ALI, and KPI BERT, the named entity recognition model, that is currently integrated in this system so that its functionality, like ALI's functionality, gets more sophisticated. And there is even further benefit for the auditor of using it by also getting for free all the KPIs that are listed in this document. So let's very briefly talk about the methodology. So I stripped away the pages where we really go into detail, see equations and all of that, just since 10 minutes is not enough, and probably I would bore you with that anyways. I mean, feel free to read the paper. It's already as a preprint on arXiv, so there you definitely get all the details. Here, I only want to stress the very high level setup. So I mentioned a couple of modules already, but to repeat myself maybe again and go a little bit more into detail, let's go through these 3 bullet points. So as the raw sentence comes in, we first need to create vector representations, ideally contextualized ones. And that is where we use the BERT-based encoder. So BERT in the NLP domain is probably currently still the most popular language model, which takes a sentence, a passage as input and provides a contextualized sequence of word embeddings, where basically not only the essence of a word is captured in the respective vector, but also the context in which this word is mentioned is captured, which is quite important. And this sequence is then the starting point for actually extracting the relevant information. And for that, we first use an RNN-based entity decoder. We also use some new concepts there, like conditional label masking, which improves the performance. I'm not going into detail here, but essentially, as I outlined already before with the example, this RNN-based decoder word for word sequentially extracts our named entities, like the KPIs, revenue, and so on, but also the numerical values, current year, and so on. And then once we have the sequence, we have a final relation decoder, which looks at all possible combinations of entities, and then simply answers a binary yes or no question to, link them or not link them. So with that, I jump right away to the experiments and briefly talk about the data that we used in this particular work. So for training and developing the model, we leveraged Bundesanzeiger documents. Bundesanzeiger is a German platform where the companies are required, all German companies are required to publish their annual reports. Hence, it's quite convenient to retrieve those. And we used 500 of them particularly and manually annotated them together with our partner PricewaterhouseCoopers in order to use supervised learning for that. So of course, this annotation process was quite costly, but in the end, it was worth it since we came up with a very nice model that worked quite well, as we will see in a second. Of course, we did some pre-processing. I skip over that now since it's rather straightforward, obviously some tokenization. And as I said, we had some other methods like regexes and so on to link these units like million, billion, 1,000 to the corresponding number so that we exactly know what is this number in fact. So here are the quantitative results of our model, which is in the bottom row. I don't go through the numbers. What I do want to stress is simply the score we're in the end mostly interested in, which is on the far right, the relation F1 score. And that is a very conservative metric because an entity pair that is related only contributes to the score, is only considered correct if not only both entities, span and class-wise, are tagged entirely correct, but also, of course, the relation has to be correct. So with that said, let's look at some actual qualitative examples. And particularly, I want to, look at point B and C here in this table. And in B, we see that there is a slight mismatch in what the model predicted in blue, in the blue span, and what was annotated, which is the red span for the KPI. And arguably, adding the word raw by the model improves actually, in my opinion at least, the extraction. However, since it wasn't annotated, there is a mismatch in the span. And as I said before, due to this mismatch, all the relations that were actually predicted for the sentence, as you can see on the right, they are wrong. Blue means, there was a false positive, red means false negative. However, only green would make our metric happy. So here, even though arguably this looks really, really good from a real human perspective, this contributes with the 0 to our metric. And that puts this already high score of over 70% F1 score into perspective. So in fact, our model is likely to perform better, like in a real perceived way. Yes, bullet point C here in the list shows a similar picture. I'm not going too much into detail. What I want to stress here maybe is that we not only have the KPI class as entity class or the current and prior year, but we also defined a DAFON class, which basically induces some kind of relationship between KPIs within a sentence. So a DAFON KPI basically means translated like something like thereof. So it is contained in a different KPI. So you get additional information just because of using that class as well. And here there was simply a wrong annotation. So the auditor who annotated that made a mistake. The model predicted it correctly, but of course it's not represented again in our metric. So some of these problems, of course, persist here as well. With that, I would conclude. So yeah, I mean, as you saw, I introduced you to our model KPI BERT, which from financial reports extracts and relates key performance indicators with the idea to, improve the overall auditing process and, reduce the working time of auditors on these rather, boring, let's say, tasks of detecting things in the report so that they can focus on the tedious details and more important issues. And as an outlook, there is, of course, the idea to extend the model to English. And also, as we saw before, we're working on developing a better metric that captures more the essence of how a human would perceive the performance. And thirdly, and that is quite nice, we want to make use of these extracted entities and relations and use them in a downstream task where we leverage, again, machine learning to automate the numerical consistency check between different occurrences of the same entity in the report. And quite nicely, regarding to this third bullet point, just a few days ago, a follow-up paper was actually accepted at a conference. Yeah, but that probably would then be something for a different talk. So yeah, with that, I would conclude. Thanks a lot.
Thank you, Lars, for this very impressive talk and results. I'm looking forward to the next one already when it's published. Thank you. So I open the floor to questions. Please feel free to write them in the Q&A chat until somebody puts a question in. Let me just take this time and ask my questions. So from experience, I know that, so I don't have a whole lot of experience reading financial reports. What I remember from them is that they are very, very long. And also from my experience of doing these kind of models, I think long range dependencies are very hard to model, especially with Word, where you have like only 512 tokens. Have you, when you look at the data, do you see a lot of occurrences where the entities are separated longer than the token length of BERT, for instance? Is that a problem, or is that only in a theoretical problem?
So first of all, what I glanced over here a little bit is that we used sentence segmentation, and that means one sentence is an independent sample. So right now, this model looks at one sentence at a time, since we're only interested to basically within the sentence to extract the KPIs. What this model is not doing, it's not like processing the entire document and tries to understand the entire document in terms of, okay, given something was written in the introduction, now there is an error here in section whatever in the very end. So these kind of things are significantly harder, since you're exactly right, BERT has a limited span of input tokens that it can process. Specifically, depending on the version, it's only 512. And if you use long sequences, you need to use other techniques, other models. In this particular case, we didn't really have cases where a sentence was that long that 512 words didn't fit. But a solution here would be either, which obviously isn't ideal, to simply trim the end, which, yeah, maybe is problematic if it happens very frequently. In our case, it happened, I think, once in the entire training data set. So for this academic exercise, we didn't really tackle that issue. And for PwC, it wasn't now a priority either. But obviously, if you want to use that for very long segments, passages, you would need to probably put an RNN on top of it, come up with other ideas. So basically try to make the range of what the model can read into memory longer. Yeah. Did that answer your question, or?
It does, yes.
Yeah.
Yes, we're running into the same kind of challenges ourselves. Yeah. So yeah, I was very interested in seeing what kind of other approaches they are.
I mean, by now, probably you're familiar with that, but there are a range of other transformer-based language models by now, like Big Bird, Longformer, you know, check out the Hugging Face library. You will find plenty of different architectures based on many different papers. And some of these, they accept token spans for up to 4,000 tokens. But even those, right, if you have a really, really long document, 4,000 is probably also not enough. So yeah, exactly. It is an issue generally with the transformer architecture. And the RNN, of course, doesn't have that problem. But yeah, again, it's a trade-off, right?
Yeah, exactly. Thank you. We have a question from the audience, from Dr. Luca Chiarabini. Sorry if I mispronounce your name. He said, I see that was used the BERT tokenizer, but the base model is an RNN. Is there a specific reason to not use BERT for token classification as the base model?
Yeah, that's a good question. I mean, I didn't go into the detail here completely. So just to explain why we did what we did. So we used BERT as simply as an embedder only, because we want our vectors to capture the essence of the entire sentence. And why do we use an RNN decoder on top of that? We use it because we want to model the sequential nature here and basically predict one token at a time, while simultaneously feeding into the previously predicted tag. So that means if my first word, let me put it differently. If I predict, okay, let's start with the first word. If I predict the first word and I get a specific tag, let's say the 0 class, because it's unrelated, then I feed a representation of this class, this we also embed, into I concatenate that with the second input representation, you know, in the sentence, in order to help the model understand what did I already predict in the past, which tags did I have in the past, because obviously the tag sequence history of my first, second, third word influences what is more likely in terms of my fourth or fifth tag, and so on. And BERT in itself is an encoder model only, so you would need a decoder which sequentially can do that. I mean, you can use BERT also as a decoder for sure, and we experimented also with transformer architectures in general to do a similar thing, what I just described with the RNN, but it turned out, since we're decoding named entity tags and not like in language generation new words from a way larger vocabulary, right? That the RNN actually in this rather simple task of named entity tag prediction performs better than the deep transformers. That was just our empirical observation, hence, yeah, the RNN. Hope that answers the question.
Cool, excellent. Thank you very much for your talk. We'll hope to see you and invite you again for the next time.
All right, thank you a lot, and have a good day. Thanks.
So moving on to our third speaker. Our third speaker is a valued member of our machine learning research team at Acodis, Dr. Moritz Platscher. He has a master's in physics from the Ludwig Maximilian University of Munich and a PhD from the University of Heidelberg and the Max Planck Institute for Nuclear Physics. After a postdoc at the same institute, he moved to Switzerland and applied machine learning to brain imaging at the Institute for Biomedical Engineering at the ETH Zurich and the University of Zurich. While looking for a real challenge after the simple use case of brain imaging, he joined Acodis and then worked on table recognition instead. He will give a short talk about our applied machine learning approaches to this problem. Moritz?
Thank you very much, Tim, for the introduction. Yes, indeed, the applications have gotten more applied, and with more application and real world, I have seen that things become more challenging. And today I will present some results that were obtained in the context of a master thesis project by our master student Pratyush Singh, who is no longer working with us, but moved on to other challenges, and I will be presenting the results of this work. So to dive into the topic, let me quickly give you a motivation and present our approach in the context and in contrast to existing approaches, and then after showing the results, I will conclude. To dive into the topic, let me start with a quote. I'm sure you've all heard this quote: "Data is the oil of the 21st century." Now, whether you like this quote or not, I think it extends one step further, because just like oil, before having any actual value to the end user, oil needs to be exploited from the earth and refined into a subsequent product. And the same is true with data, because for business users, the data is typically locked away inside documents, which is inaccessible for machines to actually make use of the data, and therefore it's inaccessible to coming up with automation processes. And this is essentially where the business value of data lies. We want to automate certain processes, just like Lars showed us with the KPI extraction and relation linking. We want to do this for more than just one task. We want to generalize this to other tasks as well. Now, this is at present really the bottleneck for automating processes, because we cannot access the data in its raw state via machines. So one thing we can do is do manual data extraction, which is, however, extremely repetitive, boring, and as Lars also mentioned, extremely error prone. So we will not only invest a lot of resources into doing something that people hate doing, but you will also curate data that is very false and full of errors. Now, what we at Acodis do is we try to leverage machine learning and artificial intelligence in order to help businesses extract data from its raw state and be able to make use of it for the subsequent refinement process. And the refinement process typically depends very much on the use case. It could be a automating of a billing process or of a payment process. It could be automating your documentation of machinery and things like that. However, the extraction from documents typically follows certain templates, because that's how we humans structure information inside documents. And most commonly, these layout cues are tables, forms, lists, or plots. And in this talk, I will talk mostly about tables. So how do we tackle this issue of extracting information from tables? Typically, this is done in a two-step process. In a first step, we have to identify, is there a page with a table? So we find all pages with tables, and then we have to segment the table on this document page. This process actually has great similarity with object detection in natural scenes, because if you look at these two examples, whether I want to find a bus or a person in an image or a table on the page follows the same logic. I am given an image and I draw a bounding box around the entity that I'm interested in. Also, if you look at the details, this is very similar between documents and natural scenes. We typically have something like 1 to 10 objects per page or image. We have rather square bounding boxes. And even in examples where we have more than one table on the page, like this one shown here, you will see that there's very little overlap or risk of overlap between different entities. Now, in the next step, what we need to do is we need to crop the table from the page. And now the task is, given the table, segment the structures of the table. That is, find all rows, find all columns, find the headers, find the subheaders that delineate the table into different sections, and therefore make it accessible for the machine to read. Of course, we need to apply OCR and extract the text information, but once we have the structure of the table, that is essentially a downstream task that can be easily solved. So given these tables, what we try to achieve is finding the structures, here shown in these colored bounding boxes, where each color corresponds to a different type of entity. For example, rows are red, columns are blue. However, conceptually, this is not different from the previous task, but we do see that there are some details that are different. We have a lot more rows in a table than we have tables on a page. There can be dozens, even hundreds of rows in a very large table. We have rather extreme aspect ratios in the sense that rows are very thin and long, columns are very thick and high, And there's high risk of having overlap between nearby entities. So we have to be very precise in making our predictions from the machine learning model. If the bounding box of a person in an image is a little bit wobbling around, we don't really care. If the bounding box of the row is, say, 0.5 centimeter up, that might screw up the entire data extraction process. And another challenge with tables is that they come in great variations. You have these large tables with a lot of structure, but you also have very small tables with just 1 or 2 rows. So what's the state of the art? Given the limited time, I'm just going to focus on one model that was proposed just earlier this year, and it was published along with a data set called PubTables 1M. This is work done by Microsoft. It was published by this year's Computer Vision and Pattern Recognition Conference. And it is thus far the most comprehensive data set for all sorts of table-related questions, namely the table detection and the table structure recognition. And most comprehensive both in the number of tables that it contains. It contains almost 1 million annotated tables, but also in the terms of the quality of these annotations. It's an extremely high quality and high quantity data set. And along with this data set, Microsoft published a model which they call the Table Detection Transformer, short DETR, which performs both the table detection and the table structure recognition task. And it is claimed that this model outperforms the classical object detection approach. As you can see here, the scores are quite significantly higher than the CNN-based approach. However, we took this model and we tried to apply it to some real world data, and what you see is quite disastrous. The model misses the header of tables, it misses rows. This table is a complete mess. There's like complete overlap between the rows. This would be absolutely useless for real world application and especially for data extraction. So an issue here is the generalizability of the models to other tasks and other data domains. So what we did, and I'm going to summarize some results and methods here in one slide because we have very little time. We have thought about what makes table structure recognition different from the table detection and the ordinary object detection. And I've hinted at it, and we've identified 3 main differences. The first is that we have a lot more entities than in table detection. So we have to increase the number of proposals, which are then refined by the faster RCNN model that we're using into the final predictions. And we see that this is a relevant quantity. If you look at the ablation study we've conducted here, increasing the number of proposals is what takes us from this intermediate plateau up to the final higher plateau. A second important ingredient is that we have to adapt the aspect ratios of the anchor proposals. Again, I have no time to go into the technical details. It is essentially the quantity that takes into account that we have more extreme aspect ratios of the detected entities in table structure recognition compared to other object detection tasks. This is the key ingredient for the table structures. And this is what you can see. It is what takes us from the bottom plateau of scores to the intermediate plateau of scores. Adding these anchor proposal aspect ratios is what is really the key ingredient for good table structure recognition. And finally, what we've done is to take account in the great variability of layouts for tables that we use deformable convolutions instead of standard convolutions. And here, an interesting observation is that they only really unfold their full power when we already have a good baseline. So in the baseline model, regular convolutions actually outperform deformable convolutions, but with the other ingredients in place, the converse statement holds. In addition to that, the examples I had shown you before indicate that the model was trained without data augmentation. So what we do is we take an input image and its segmentation, and we perform all sorts of augmentation. We flip the table, we modify the intensity so as to be able to also handle poor quality documents. We stretch and squeeze the table. We crop subtables from the original table, and we add random amounts of white space around the table, all from the same image. And finally, we combine this into an entirely new training sample, and therefore we expand this already very large training set into an even larger training set. So let me give you the results. What have we done? Well, we're a small company. We don't really have the resources to train a large model on 750,000 training samples, which is the amount this data set contains. So what we have done is we've taken a subset of 150 images, trained for 30 epochs, and then fine-tuned for another 5 epochs on the full data set. And what we see then here are the results that we obtain on the full test set that is unseen data during training. And you see already our convolutional neural network based on the 150 samples is slightly outperforming the table detection transformer proposed by Microsoft. And after the 5 epochs of fine-tuning on the full data set, we are significantly outperforming the table transformer proposed by Microsoft in all scores, but most notably in the average precision. This is also true for the individual categories. You see that it's not simply one category that is most prevalent in the tables that outperforms the table transformer, but we're actually better at detecting all the subcategories of table structures in this test set. So how does it look in practice? Well, here are some examples from the test set. This is an example where debtor predicted an extra column. Our model did not, so this is actually a very good prediction. The second table is one where the row alignment is a bit off in our case. There are symbols in these rows that would be missed in data extraction, so you'd have to actually do some post-processing to get this data. That's not perfect. Debtor does a good job on this table. Here's another approach where our model, well, the row alignment isn't perfect. In this case, it would not be an obstacle for data extraction, though. However, debtor here completely misses entire rows. There's no prediction here. There are overlapping rows in the bottom part of the column. And as you might notice, these light blue rows, which are table section headers, and in this case, split the table into different age groups, smoker, non-smoker, male, female subgroups of the participants of this medical study. These are missed, so you would actually miss the entire structure of the table. Another result which looks similar, our model here predicts a very uniform structure, whereas debtor again misses rows and predicts these overlapping rows and misses the table's substructure headers. So how does our model perform in the wild? I showed you 3 tables before where debtor failed. This is the prediction of our model on these tables. This is a completely different data set, completely unseen data. You see on the left 2 tables, we actually have excellent results. This would be correctly extracted in a downstream data extraction part. However, the right table is indeed a challenge. It's already a lot better than what debtor predicted, but you see this, mixed vertical and horizontal font, one empty column. That's a very confusing to our model. Here we actually miss a few data points in the row. So this is a very challenging table for all kinds of model, but we've already found some improvement over the current state of the art. So with this, I would like to summarize. We've proposed a standard convolutional neural network-based table structure recognition model, which outperforms what is claimed to be the state of the art with transformer architecture by leveraging the task-specific requirements in the model architecture of our model. We've used extensive data augmentation and more training data in order to reach these excellent scores. And we have achieved state-of-the-art results, both under lab conditions, but also out in the wild. And so some future research directions here are, can we incorporate more real-world data to also tackle these challenging structures that I just showed in the last slide? And can we maybe also refine the transformer-based approaches in the future? And with this, I would like to thank you, and I'm happy to take some questions.
Thank you, Moritz, for this nice summary. I know how long this entire project has taken you from my own experience. Please, audience, if you have questions, feel free to put them in the chat, in the Q&A chat. Maybe I can start with an easier question. Looking from this, we see that the data has a huge influence on the performance of whatever you get trained. Do you feel that the transformer would help, and what kind of advantages would that bring? Trained on the same kind of data and augmentations?
That's a good question. That's a question I cannot answer because I haven't done it. But I think it's an interesting question to see if transformers are more generalizable than convolutional neural networks. What we've seen is with the training strategy that Microsoft applied to the model, it does not generalize well. But since they did not use extensive data augmentation, that actually might be just the one missing piece. And whether or not you can transfer certain task-specific learning, such as the aspect ratios or not, into the transformer-based recognition model, that's also an interesting question that has not been investigated to the best of my knowledge.
Thank you. Are there any questions from the audience? If not, taking a look at the time.
I would have one. If
okay, sorry, I didn't see you raising hands.
Just out of curiosity, has someone tried the same task, but not with a vision input, but with a hopefully very good OCR input? So basically neglecting colors, boldface, like these vision inputs that a human probably also uses and the machine as well to detect the structure, but instead of using that, using maybe more also positional information for sure, but specifically also the content, like maybe a model can take something from that as well. And
yes,
maybe
so
there are even ways to combine both, using a vision and somehow also the NLP side, you know, getting something out of the words themselves that are present.
Yes, absolutely. So I think there are two approaches that go in this direction. One is based on graph neural networks. So you take the text input and the position input, and you try to predict the relation among the different entities, the text elements in the table. That does, to the latest of my knowledge, not yet work very well. Mostly because of a lack of annotated data, because you need a very specific type of labeling the data in that case. And you need sort of a relation among the different table elements. And the other approach is using language models to predict, say, the column ID or the row ID for a given word, which also works okay-ish, but again, it's sort of a lack of annotated data. So what we have here is a lack of data that's sort of limiting the research. And then on the other end of the research pipeline, it's really hard to compare these models, right? If you can just really do it by anecdotal comparison, you can extract the information and compare either, I don't know, F1 score on row ID, column ID, or in our case, you can predict bounding box overlap and measure your metrics based on this. But how you connect these two is, I think, not really done in the literature. So it's very hard to compare the approaches. There are different approaches to. My understanding is that the vision-based approach is currently the one that works best, that generalizes best. But there's certainly room for improvement, especially also taking into account multimodal approaches, as you hinted.
Yeah, thanks.
Excellent, thank you. And then looking at the time, we'll move on to the next speaker. Thank you, Moritz, again. Our final speaker is Severin Kappeler, technical product manager at Acodis. Before he joined our research team, he was the CEO and founder of his own IDP startup. So he brings a lot of expertise to our firm as well in starting up an IDP firm. He has also worked as a senior forensic technologist at Deloitte. He has a master's in mathematics from the ETH Zurich. And in this talk, he will showcase a real-world application of the expert mode of the Acodis software. Severin?
Thank you very much, Tim. I hope you can all hear me. And yeah, so my part will be, I guess, the most business-like part. And I'm just going to share my screen to show you our platform very quickly. There we go. Perfect. So I'm here today to show you how we from Acodis leverage all these exciting innovation that comes out of our research lab to actually solve real world data problems of companies. And what we've experienced really over all these years is that every use case of all the companies have, they're so unique, and every document is so different that like the only approach that we really saw was working was a customized and a tailored approach to the use case. But what's the problem with this approach, like making it so tailored? The problem really lies that the insight, the business knowledge, typically it doesn't lie with the CEO of the company. It doesn't lie within so does the machine learning expert also doesn't know all this information. And it's definitely also not us from Acodis who has the business insight. So the business insight is with the auditor for the financial reports, for example, or it's with a contract manager for contracts, or it's with the chemist for some safety data sheets. So it's with the business expert, this knowledge that's so valuable that we need. So therefore, we Acodis, we've came up with a platform, the Acodis IDP platform, that's at the same time offers flexibility, transparency, and easy to use. Flexible, so you can adjust it seamlessly to your use case. Transparent, so that you're always in the driver's seat as a user and you always see what's going on to also comply with regulations. And easy to use, that with just a click of your mouse, you can create sophisticated AI automation workflows. So that's the idea of our platform. And let me show you how that looks like. So here we have the Acodis IDP platform. And just with few clicks, I was able to create 2 workflows here. So you see, I have one workflow here I created for invoices and batch records. So I can just like stream documents through. I can define where they come in, how they get out, what data needs to be extracted, what am I interested in. But the case I want to focus on today is one I really like personally, a very complex type of use case, which is with so-called safety data sheets. So I created a workflow for safety data sheets. And before we start, let's just like quickly have a look at what this use case is about. So let me open here this document, this safety data sheet that's publicly available. So if you think of a chemical company or a pharma company, they deal with a lot of substances and products. And all those products, they typically are shipped with a so-called safety data sheet. And when you work with these products and those ingredients, you have to make sure, in order to maintain the safety at your workplace, you have to make sure that you read all this information and combine it for all the substances you're using. So for example, we have hazard statements in those. We have like a revision date that's probably important as well. You have the name of the substance. Like there are many different information in this document. Also, we have hazard statements in form of pictograms. All this information is necessary to understand when you work with these substances. And you can imagine there are tons of them. So you work not with just one substance, but typically with hundreds, if not thousands of them. And so you have to find ways to quickly process that. And the problem is also not just extracting this information. For us humans, this is quite easy to read, but for a machine, you can understand like it's not so easy to extract the relevant bits of this. So some information is just text somewhere in it. So for example, we have here the trade number, the revision date that might be a bit more intuitive for a machine, but then some of the information is just a picture. So you need to be able to interpret that picture. Then obviously we have titles like this one. So the title might also be relevant in order to understand the safety data sheet correctly. And also we have, like Moritz mentioned before, we have tables, obviously. So in order to extract the CAS number correctly, we need to understand first the table structure. We cannot just read it line by line like an OCR engine would do. And that's why we came up with a very modular and very easy to use approach to deal with those documents. And let's just do that very quickly together. So we offer you complete transparency on what we already understood from this document. So on the right, you see kind of what the machine understood based on what you told the machine to do. Currently, there is nothing because we haven't told the machine a thing. So let's just start by giving the machine very simple instructions how to do that, by just adding steps, step by step. So the first thing is typically we add native text. So we tell the machine, go ahead and process the text that's inside this document. But this is obviously not enough. So if you look at the right, this is pretty much what you get out when you just OCR this document. So it's just like line by line, not very useful. So the first thing we might think is, okay, we have a lot of unnecessary content here, like these header information, also the repeating page number, not really necessary. So let's just add a noise step, and we need to specify what we mean by this. And this is as simple as we select it and we choose this we don't want. It disappears from here. We can also let this number disappear. And we don't want to label every single document and every single page, because we know that's a very tedious process. So we help you. So already then the machine kicks in and tries to assist you in this labeling process. Then let's say we want structure. We need to understand these titles. So let's add a structure step. Again, we specify it. So let's say that's for me a title. And this also is for me a title. And as I'm doing that, you can see I'm building here a table of content for this document. So this is very specific to this type of document. So I'm seamlessly creating this for you. So as I go along, you can see how this table of content develops and grows. So it already starts suggesting me new stuff. So to again, help me in accelerating this process. I can then go ahead and also add more steps, like the one Moritz mentioned. So obviously we have tables. So we also want to understand tables in this one. We want to understand images. So let's add an image step. And by doing that, we slowly evolve this initially very unstructured way the machine understood this document into a more structured form. So behind this, there will be obviously an XML that's very machine understandable and very easy to process. So by just adding these simple steps, we create an analysis that's dedicated and specific to these safety data sheets and specific to our use case in the end, how we want to use that document downstream. We can also add another step to aggregate the text to make sure the text is correctly grouped, bullet points are recognized, all these kind of things. So that's how you work with the Acodis ITP platform. Very simple. You give the machine instructions, what it should do, how it should process this information, and you specify for each of those steps how you interpret it. And with this efficient and very easy to use way, we can now build very customized and tailored AI models. And let's have a look how this looks like. So I've used here just 5 training documents, 5 safety data sheets that have more or less a similar structure, but completely different content. It varies, it has different amount of pages and different layouts of tables. And I was able to create a model from that. And let's have a look how this applies in real world. So here I'm opening a new document. The machine has never seen that document. I've just freshly uploaded it to the platform. And we can see we can already open it now within this new analysis we created specifically for safety data sheets, specifically for our purpose. So you see we have here the safety data sheet number that we try to discover. We also have the structure, we have noise, and we have some other tags here that we apply. And initially, now the machine hasn't dealt with this document. So now again, this is a very unstructured view here we have on the right. So the machine doesn't really well understand it yet. So let's apply the magic. Let's apply the model we've trained on 5 documents only to see how the machine is already able to understand this document. So all I do is apply model. It runs for a couple of seconds. It uses all the information I fed it to as the business user to read this document correctly. So this runs for a couple of seconds and comes then back with the outcome. It's supposed, so it actually goes through, it reads the native text, It's detecting the SDS number, the safety data sheet number, removes the noise, finds the structure, detects tables as well, and the other steps here that it's supposed to find. Very good. So, and let us like give it a couple of seconds to finish. Obviously, that was quicker when I tested it initially, but it's always like that. But yeah, so essentially we were able to create this very custom workflow, this custom set of steps for this type of analysis, for these specific safety data sheets to manage that. And there we go. So now we see the content here adapted. So now it's really in a much more structured way. So you see headers have been detected. Also noise has been found here. And as we scroll through the output, we also see that those hazard statements, those labels were detected. We also have tables in here that were correctly aggregated and embedded in the content. And like this, we were able, with just 5 documents, to find a very structured way of representing these documents and use it for downstream. And also, because transparency is very important for us, we don't just give you kind of a quality check to see where it actually works, but you have full control over how the model is already performing. So at every point in time, you can actually look at the documents, at the models, to see where we stand. And you see, based on just 5 documents, using our powerful pre-trained models, the model was already able to reach accuracy scores of 80% and above, F1 scores, for all those individual steps. So we were able to create a sophisticated, dedicated SDS safety data sheet model, and this with a single line of code with just a few clicks. Thanks very much. So that was it from my part. Very quickly, I'm very happy to answer some questions and open the floor to the Q&A. Thank you so much.
Thanks, Severin. I'm always impressed about our own software, strangely enough, about how it works. Yeah, like as Severin said, we're open for questions. While we're waiting for some questions from the audience, let me ask a question. What kind of customers or clients do you specifically see using this particular the part of the software?
Thanks so much. Yeah, that's a very good question. So, well, in general, because our tool is so flexible with all these like steps, these modular steps, it really applies to many different industries. But the industry where we see the most traction right now, and also the biggest, let's say, return of investment or quick return of investment, is in the health sector and also chemical industries, where there is a lot of paper documentation, a lot of product-related documents, as we call them. So like these safety data sheets, but also some like batch records, all the stuff that's related to a product workflow. All these documentations, then they really are there available in huge masses. So it's really important and necessary to automate these processes. And also the information we want to get out of this is also relatively standardized. So we typically always want to get like these hazard statements. We always want to get these pictograms. So that way it's very, it's a perfect use case for our software to tailor it to those specific use cases.
Thank you. Well, final question, I guess, for me. I see this is the expert mode. Do we also have a less sophisticated / dummy mode for
Yes. So, I mean, like how we see that is really kind of in 2 ways. So what we've seen here is the expert mode really focusing on complex documents like safety data sheets. We also offer like 2 types of workflows. We call them like just the regular data extraction workflows and the custom workflows in the expert mode we just saw. I have here one workflow that's a bit more, let's say, focused on extracting just individual data points of more standardized documents, like invoices is a great example for that. So you have, they follow more or less the same structure, and you can find the amount more or less in a similar place of the document. And you're talking typically also not of very long documents, but maybe few pages only. And that's also why we have a different way of approaching that, which is a more linear workflow, and that's what we call the assisted mode. So we also offer that.
Thanks a
I
lot.
also would have one question if we have time.
Yeah, sure.
First of all, what OCR engine do you use? Can you disclose that? Or, I mean, I guess it's not something you developed yourself, since OCR engines are typically little involved. I don't know, maybe I'm wrong, but there are already good ones out there. So I'm just curious.
Yeah, very good question. Yeah, so the answer is, again, so we focus really on this flexibility part. So in the end, you can, with just a few clicks through the user interface, you can hook up your own OCR engine yourself. The one we use standard, so it's correct, we don't do it our own because there are others doing that for a long time.
Right, I mean.
And so we use currently Microsoft Azure, like cognitive services for that, which has been proven to be at least from our heuristic experience, to be the most efficient and most accurate one. But there are obviously others out there. We even thought about some approaches where we could combine different OCR engines to make sure that, like, where it's really critical to get it right, to combine this and use an approach like that.
And then, similar to my question before to Moritz, in order to detect the structure and all of that, I mean, of course, I get that the user annotates certain things like once or twice, and then the model already kicks in, makes suggestions and so on. The input here is, again, a vision input, similar to what Moritz showed with the tables, or are you actually using the OCR input already from the native text along with that? Like, can you maybe talk a little bit about that?
Mm-hmm. Yeah, very good question as well. So it depends on the step. So like we have different ways how we what we use as data for our models, so there are some of the steps which are purely text-based. For example, like noise is like a classic one. So this is typically just like depending on the content. So here we don't use any optical features, or let's say, so we actually do. So what we use, not just like the embeddings and like the semantic understanding, but also like the positional data, layout information. So we use all that. Then for tables, as Mari said, there we use purely optical features. But then also for structure recognition, it's very important to also understand like the layout, the format of the text itself. Titles typically start with something like section 1.1. So depending on the step, we use different set of features.
So I guess you combine bounding box information for certain passages along with the actual words that are contained there, right? Because the bounding box information is already numeric, and it gives you a good idea about where something is located.
Yeah, again, depending on the step, yes. But that's kind of the basis for the more classic steps. Yeah. So this is also this makes the process much more quicker. So also you want to make sure that you don't train stuff for hours and hours. So whenever possible, we try to use classical models because they're faster, and if it works, it's also quite accurate. But then for more sophisticated, complex steps like structure, we use deep learning, which then also takes a bit longer, but also can take into account semantics.
Yeah, thanks a lot.
Thank you.
Excellent. Thanks again, Severin. And with this last talk, we close the webinar. We would like to thank our speakers again, Professor Andreas Fischer, Professor Lars Hillebrand, Moritz Platscher, and Severin Kappeler for their excellent talks. We thank the Data Innovation Alliance for their support. We at Acodis are on a mission to turn any document into structured data in seconds. So we are especially invested in the field of document AI, where academia and industry can meet at the edge. So don't forget to check out their Data Booster program if you're interested in academia industry collaboration yourself. We are happy to mediate between or join a Data Booster program as well from the industry side. I would also like to thank the marketing team and the sales team at Acodis for organizing the whole setup here, especially Simon, Nicole, Mitchell, and Dream. And finally, don't forget to fill out your surveys when you exit the webinar. Thank you very much for joining. I wish you all a good day until the next time.